Students, today we are going to perform experiment number 7 of power system operation control. The title of the experiment is to study two area load frequency control. For this experiment we will require MATLAB Simulink software. Now we will see the theory part of the experiment. Pool operation. An extended power system can be divided into a number of load frequency control areas interconnected by means of tie lines. Such operation is called a pool operation. The basic principle of pool operation in the normal steady provides: first, interconnected areas share their reserve power to handle anticipated load peaks and unanticipated generator outages. Second, absorption of own load change by each area. Here two areas are shown, they are connected by tie lines. Now we will see the complete block diagram representation of two area load frequency control. Consider the complete block diagram representation of for single area, area 1, this is for area 1, this is for area 2. These two areas are connected by the change in the frequency, difference in the frequency at this point. After we will add the integrator, then the tie line is connected by using synchronizing power coefficient. This will become the complete block diagram representation of two area load frequency control. Now we will see the numerical based on two area load frequency control. A two area system connected by tie line has the following parameters on a 1000 MVA common base. Area 1, 2, speed regulation 0.05, 0.0625, frequency sensor load coefficient 0.6, 0.9, inertia constant 5, 4, base power is same for both the areas, it is equals to 1000 MVA. Governor time constant 0.2 second, 0.3 second, turbine time constant 0.5 second, 0.6 second. The units are operating in parallel at the nominal frequency of 60 Hz. The synchronizing power coefficient is computed from initial operating condition and is given to be PS is equals to 2 per unit. A load change of 187.5 megawatt occurs in area 1. First, determine the new steady state frequency and the change in the tie line flow. Second, construct the Simulink block diagram and obtain the frequency deviation response for the condition in part 1. Now we will find out the new steady state frequency. Before that, we will find out the per unit load change in area 1 is given by change in PL1 is equals to 187.5 divided by 1000. Here 187.5 is the total change in the actual change in the load at area 1 and 1000 is the base MVA. So, it is in per unit given by 0.1875 per unit. The per unit steady state frequency deviation is given by change in omega SS is equals to minus change in PL1 upon bracket 1 upon R1 plus D1 plus bracket 1 upon R2 plus D2. We will put the values into this equation. We will get omega SS is equals to minus 0.1875 divided by into bracket 20 plus 0.6 plus bracket 16 plus 0.9. So, change in omega SS is equals to minus 0.005 per unit. This is the change in the frequency in the per unit. We will convert into hertz by multiplying the 60. So, it is minus 0.3 hertz. So, this much amount of change we observe after the 187.5 megawatt load is change in the area 1. We observe the change in the frequency equals to minus 0.3 hertz. The new frequency under this condition is given by f is equals to f0 plus change in frequency. Here f0 is the nominal frequency. In this case we have taken 60 as the nominal frequency. So, minus 0.3 it gives us 59.7 hertz, the actual frequency of operation after the change of 187.5 megawatt load change in the area 1. Now we will solve the change in mechanical power in each area. So, first area gives change in PM1 is equals to minus change in omega upon R1. Omega is in first area is minus 0.005. So, R1 is 0.05, it gives 0.10 per unit. In second area it gives minus 0.005. This is the change in the frequency, steady state change in the frequency in per unit. This is the steady state change in frequency in per unit. In area 1 speed regulation, area 2 speed regulation, it will give you the per unit change in mechanical power. So for area 1 it is 0.10 per unit, area 2 it is 0.080 per unit. So in megawatt, when you multiply these two values by 1000 base MVA, when you multiply these two values by 1000 base MVA, you will get the values in megawatt. So 100 megawatt in area 1 and 80 megawatt in area 2. But you just observe that area 1 increases the generation by 100 megawatt and area 2 by 80 megawatt at the new frequency, new operating frequency of 59.7 hertz. So 59.7 hertz, the generation 1 increased by 100 megawatt and generator 2 increased by 80 megawatt. The total change in the generation is 180 megawatt. As you can observe here, total change in the generation is 180 megawatt, but which is less than 7.5 megawatt. Actual demand is 187.5 megawatt. So actual demand in the system was 187.5 megawatt and total change in the load, total change in the generation was only 180 megawatt. Because of that, we observe the change in the frequency of 0.3 hertz and new operating frequency drops from the 60 hertz nominal value. Here the new operating frequency is 59.7 hertz. Now the change in area 1 load is change in omega into d1. It is given by minus 0.005 into 0.6 is equals to minus 0.003 per unit. So it is minus 3.0 megawatt, and in second area it is given by 0.0045 per unit. In megawatt it is given by minus 4.5 megawatt. So the total load change in the area is minus 7.5 megawatt. So tie line power flow is given by change in P12. Here you observe that the direction is P12 is shown. So the sign of the answer will be negative in this case. So it is 0.084 per unit. So that means 84.5 megawatt flows from area 2 to area 1. So P12 is equals to minus 84.5 megawatt. Here change in P12 is minus 84.5 megawatt. Power is taken from the area 2 to area 1 to satisfy 187 megawatt of change in the power at area 1. 80 megawatt comes from the increased generation in area 2 and 4.5 megawatt comes from the reduction in area 2 load due to frequency drop. Now we will perform the experiment in the MATLAB Simulink software. Open the MATLAB Simulink software. This is the home screen of the MATLAB Simulink software. Go into the file menu, new model. First we will obtain the complete block diagram representation for area 1. So for that, go into the Simulink library browser. Here we will take the gain, we will add gain as we required gain, rotate this gain, then we will require scope, so add the scope, then we will require transfer function, so we will add transfer function. We required for one area we required 3 transfer functions, so copy paste 3 times. Now math operations. In math operations you will find the sum of elements, put here minus sign, then we will require the subtraction block. Here, after that we will require only the step input, add step, add here. Now connect all the blocks. Again, this is the complete block diagram representation of system 1. Now we will change the transfer functions as per the example given. So transfer function, for transfer function we will see the data of that example. So governor time constant it is 0.2 and turbine time constant it is 0.5. Change speed governor time constant (0.2) and turbine time constant as 0.5. Then we have D1 is equals to 0.6 and H1 is equals to 5. So we will add in the third generator 5 into 2 10 0.6 0.6. Then govern speed regulation it is 0.05. So it is calculated as 20, 1 upon 0.05 it is 20, 1 upon 0.05 or you can directly put there 20, as the speed calculated change in the power demand calculated in first step it is 0.1875. So we will write steps input, initial value 0.1875, final value 0.1875 at step time 1. So we will run the simulation. This was the output of control area 1. Now we will do the same procedure for control area 2. Just copy this whole and paste for one time. Change, delete this, change sign to plus, then just change the values as per the example. So for area 2, Tg2 time constant of governor 0.3, 0.6, 0.3, change the values 0.3 and 0.6. Last 4 and 0.9, H2 is equals to 4 and D2 is equals to 0.9. So 4 into 2, it is 8. Here you will have 0.9. So then we will require to change the regulation, speed regulation. Speed regulation for second area, it is 0.0625, it is calculated as 16. So here you will put the 16. Here you just will change the value 20. Now here onwards we will put the summation block to have the changes in the frequency. Just rotate this block. Then we will add one integrator. Rotate this integrator block. Then we will add the constant block for synchronizing coefficient. So commonly used block, you will find the constant block. Add constant block, rotate this block, sorry, we will require gain. So change the gain to 2 as the synchronizing power coefficient is given as 2. Then connect. Here before connecting it, add minus. So connect this terminal to minus, connect this, so the circuit will become complete. Now check the scope. So you will find the change per unit change in the frequency as in our example, as we have solved earlier. It is minus 0.05. So you can observe it is approximately minus 0.05 change in the frequency. In per unit it is minus 0.05. So here this is value minus 0.06 and 0.04. So it is around 0.05. You can just observe the values that we have calculated. So change in the frequency in per unit it is minus 0.05. After steady state frequency deviation in hertz, how to calculate? By multiplying 60. So we will get 60. It is minus 0.3. So for that purpose we will require one constant block. So make this 60, put one scope to So we just add the gain block, rotate this gain block 60, then add the scope. You will get the frequency in hertz, change in the frequency in hertz. It was 0.3, so it is 0.3, around 0.3. This is minus 0.3. Now the actual frequency we will take. So for that we will require the summation block, rotate this block, so add here plus plus sign, and add one constant block, change its value to 60, add one scope. This will give you the actual frequency or new frequency. It is 59 point something hertz. So 59.7 hertz, you will observe the value. This is 59.7 hertz. This is at 59.7 hertz value you have got here. Next is to find out the tie line power. So for tie line power, you will get one scope, connect here. This will give you the tie line power. So in per unit, the tie line power is around 84 megawatt. So minus 84 megawatt. Minus 84 megawatt. P12 is minus 84 megawatt. In megawatt, if you want to find out in megawatt, just multiply by 1000. Now we will see the change in mechanical power in each area. So it is the answer is in one area 1 is 100 and area 2 is 100. So first we will find out in per unit basis, then we will find out in megawatt. So for per unit basis, you just so this block gives us the mechanical power, change in mechanical power. Connect this block to this here, change the base to 1000, change this base also to 1000, connect this block also to area 2, add one scope, change the axis properties to 2, so that we will add 2 scope, so area 1 has 100 and area 2 has 80. So here is the answer, 100 for area 1 and 80 for area 2. This way you can perform the experiment on 2 area load frequency control. I have one block, I have one model already prepared, complete model already prepared. So we will see that model. two area load frequency control. So here we will observe the various graphs. A complete model. This is 100. The change in the mechanical power in area 1 it is 100, area 2 it is 80. Then area 2 frequency. First graph shows the drops in the frequency, steady state frequency deviation in per unit, steady state frequency deviation in hertz, and third graph shows the change in the frequency, new frequency in hertz. So from the 60 it decreases for area 2 when the load of 187 megawatt is applied or increased. Similarly for area 1 we will see all the graphs at a glance. So area 1 per unit it is 0.05, minus 0.05, minus 0.3 and 59.7 hertz. So this is 59 actual frequency of operation, 59.7 hertz. Then tie line power in per unit it is minus 0.084. So this way you can study the two area load frequency control.